All right, let's get into it. We spend a lot of time in math talking about straight lines. They're simple, they're predictable, but the real world, it's not made of straight lines. It's filled with curves, arcs, and all kinds of paths. Today, we're going to crack the code on those curves. We're talking about the mathematical blueprint for them, the quadratic function.
I mean, really think about it. That perfect arc of a basketball heading for the hoop, the way water sprays out of a sprinkler, even the shape of the satellite dish on a roof, they all follow the same fundamental, beautiful path. And the secret to how we can predict and even design all of those things? Yep, it all comes down to understanding quadratic functions.
So where do we even begin? Well, like with any complex structure, you've got to start with the basic blueprint. And for every single one of those curves we just mentioned, the blueprint is this surprisingly simple equation: y equals ax squared. That's it. This little formula is the key that unlocks everything else.
And here it is. This is kind of the parent of all parabolas. Y equals x squared. Just look at its clean, simple U-shape. It's perfectly symmetrical, sliced right down the middle by that vertical y-axis. And see its lowest point? That's called the vertex. And for this basic version, it sits right at the origin, the point 0, 0. Seriously, every other parabola we'll look at is just a version of this one.
Now, let's talk about that a in our blueprint. The best way to think about a is like a stretch or squish control. When a is a positive number, the parabola opens upwards, kind of like a bowl. But watch what happens as a gets bigger. As we go from 0.5 to 1 to 2, whoosh! The parabola gets squeezed. It becomes much narrower and steeper.
So what happens if a is negative? Well, this is where it gets really fun. A single minus sign completely flips the script. The entire parabola turns upside down. Suddenly, our bowl is an umbrella. And that same stretch rule still applies, but to its absolute value. A number like -2 makes for a much narrower curve than, say, -1/2. Okay, so let's do a quick recap. The sign of a, positive or negative, tells us if it opens up or down. Easy. The size of a tells us how skinny or wide it is. And for this basic y equals ax squared form, the vertex is always locked at the origin, and the y-axis cuts it into two perfect mirror images. So we've got our shape down. We can make it open up or down, make it skinny or wide, but there's a small problem. It's stuck at the center of the graph. How do we get it off the origin? How do we move this thing around and place that curve anywhere we want? Well, it's time to upgrade our blueprint. And here is our upgrade. This is called the vertex form. Now, I know it looks a little more complex, y equals a times x minus m squared plus n, but don't let that fool you. This thing is incredibly powerful. Just think of m and n as your personal control panel. M is like a slider that moves the parabola left and right, and n is the slider that moves it up and down. It gives you total control. And the process is actually super straightforward. You take your basic shape, y equals ax squared, you slide it sideways by m units, and then you slide it up or down by n units. And just like that, the vertex, which started at 0, 0, is now at its new home, the point m, n. And check this out, it's a perfect illustration. You can see the original ghost graph of y equals 0.5x squared sitting at the origin. We then shift it 2 units to the right, and then 3 units up, and look where it lands. Its new vertex is exactly at the point 2, 3. And you can just read those numbers right out of the equation. Let's look at one more just to make sure it sticks. For the equation y equals 2x plus 2 squared minus 3, we can immediately spot the vertex. Now remember, the form is x minus m. So to get x plus 2, our m must be a -2. And n is clearly -3. So bam, the vertex is right there at -2, -3. And that vertical line passing through it, that's our new axis of symmetry at x equals -2. It's all right there in the equation. Okay, now for what I think is the really cool part. This is the moment where the picture on our graph connects directly back to classic algebra. We're going to talk about where our curve crosses that horizontal x-axis. Here's the big aha moment. Every parabola we've looked at can also be written in what's called standard form, y equals ax squared plus bx plus c. Now, when does the parabola hit the x-axis? Well, that happens when its height, y, is 0. So we set y to 0, and we get that classic quadratic equation. Those intersection points on the graph are the actual solutions, the roots to that very equation. The picture and the algebra are just two sides of the same coin.
But what if I told you there was a secret code hidden inside that equation? A secret that lets you know exactly how the parabola will interact with that x-axis without ever having to draw a single point of the graph.
This is the central question, right? Is our curve going to slice through the x-axis at two distinct points? Will it just come down and sort of kiss the axis at a single point, or will it miss the axis entirely, just floating above or hanging below it?
The answer lies in this powerful little tool called the discriminant, or just D for short. It's a single number you calculate from the a, b, and c in that standard form equation. The formula is simply d equals b squared minus 4ac. And this isn't just a random calculation. It's like a crystal ball that tells you the future of your graph. And this slide says it all. Look at this direct comparison. On the left, you have the three visual possibilities: crossing twice, touching once, or missing entirely. On the right, you have the rule. The sign of that one number, d, perfectly predicts which of those three pictures you are going to get. It's fantastic.
So let's lock this in. If the discriminant, d, is a positive number, you are guaranteed to have two distinct x-intercepts. If d is exactly 0, the vertex of your parabola is sitting perfectly on the x-axis, giving you just one intercept. And if d is negative, your parabola will completely miss the x-axis. No intercepts at all.
And this is why it matters so much. It's an incredible shortcut. Instead of plotting a bunch of points and drawing a whole graph, you can calculate one number and instantly understand a critical feature of that graph's behavior. It's a perfect blend of algebraic power and geometric insight.
So now you have the tools, the basic blueprint, the controls to move it anywhere, and the secret code to predict its behavior. The next time you see a curving bridge, a water fountain, or even just a bouncing ball, ask yourself, could that just be another parabola in disguise? Thanks for watching.